Hi everyone, welcome to this tutorial on vector equation of planes. In this video series, we are going to explore how to describe planes in three-dimensional space using vectors. When we talk about planes, planes are fundamental in geometry, physics and engineering, and understanding their vector equations can help us solve a variety of problems involving 3D shapes and spaces. So exactly what exactly is a vector equation of a plane? Now, simply put, it's an equation that let us represent every point on a plane as a combination of vectors. So when we talk about vector equations of planes, we are talking about equation that lets us represent every point on the plane as a combination of vectors. And so the in our discussion or throughout this tutorial, we will break down the equation step by step. We will learn how to find these vectors from given information. We will work through examples to construct vector equations of planes and also visualize planes in 3D space to better understand their orientation. Alright, so by then you will feel comfortable working with vector equations of planes and also apply them to both mathematical problems and real world applications. Alright, so now let's begin. Vector equations of plane. We are saying that a plane is defined as a surface such that the line joining any two points on it lies completely on the surface. So a vector normal to a plane satisfy or specify the direction. And we are also saying that equation of a plane passing through a given point and perpendicular to a vector or so in equation of a plane passing through a given point and a perpendicular vector, we are saying that assuming that we have a plane that passed through point A whose position vector is A with respect to O and then is perpendicular to the given vector M, then we have our AP to be perpendicular to N. So that is what is exactly happening here. If you have a vector, a point which is A, and this point is in a plane or is in this plane, and there is a normal which is also perpendicular to the point to the plane, then we are saying that if P is also any point on the plane and it's having a position vector of R, then if we join A to P, we form a line. For that matter, vector AP is perpendicular to vector N. So the joining of point A to point B creates another one, and that point AP is said to be perpendicular to N. And for perpendicular vectors, we've already said that if two vectors are perpendicular, then it means that the dot product between the two vectors is equal to 0. So from our previous lesson, we said that the dot product of two vectors is equal to 0. So if you have vector AP dots, the normal, the end which is perpendicular to A or to the plane, then we are saying that the dot product between these two will give us 0. But we know already that AP is the same as OP minus OA dots all dots N is equal to 0. But we already said that the position vector of P is R. So in place of OP, we put R there. And then the position vector of O is A. So that one we put A there. All dots N is equal to 0. So when I do an expansion here, it means I'm going to have R dots N minus A dot N equals 0. So that is exactly what we have here. Alright. So we are also saying that the form of this equation that I have here, R dot n minus a dot n equals 0 is called the vector equation of the required plane. That is the non-parametric form. Now let's talk about Cartesian form of this equation. Assume that x1, y1, and z1 are the coordinates of A, and then A, B, C are the direction ratios of then A, which is x1i plus y1j plus z1k, and the normal to perpendicular to the plane is also having AI, BJ plus CK, and R is equal to XI plus YG plus ZK. Then we are saying that since we've already established R minus A dot N equals to 0, when we substitute the values, the components here, then it means that for R to be XI plus YG plus ZK, we will just put that one here. And we already know that we are subtracting A from R. So if you have XI, X1I, X1I, then the corresponding one we are going to subtract is XI. So when you put this together, we are going to have X1 minus X or I. And that is what you have here. Okay, so R is the X here. And then our A is what? X1. So it's going to be, it's going to be X minus X1I. Sorry. Okay. And then the second one too, we pick this one, Y1 and then Y1J and then YG. We are subtracting A from R. So we are going to have YJ written first minus Y1 or J, Y1J2. So we put J out. So we're going to have Y minus Y1 or J. And that is what we have here. Plus, then the last one is Z minus Z1K. And then here we are saying that all dot N. And our N is AI plus BJ plus CK equals to 0. Alright, so when we multiply through by ABC, then it means that we are going to have A, because we've already established that if we have dot A1, if let's say we have 1, 2 dots, 3, 5. We've already established that if you have a question like of this nature, then it means that we are going to dot 1 to 3. We are going to have 1.3 plus 2.5. So in this case, you are going to have 13 as your result. So the same thing is happening here. If you dot this one to this, means you are going to multiply this by this correspondingly. If you take this one to, we are going to multiply it by this. And that's what you have here. And if you take this one to, we are going to multiply it by the C. All equals 0. So of course, AX plus BY plus C is equal to B. And this is the Cartesian equation of the plane in non-parametric form. Now the vector equation of the plane passing through the origin and perpendicular to the vector is R dot N equals 0. Now let's take a question. Find an equation of the plane through the points 2, -4, -1 with the normal vector N equals to this. So we've already established that the vector equation is x minus x1 a plus b y minus y1 plus c z minus z1 equals 0. And we know that this one represents our a, and then our a equals to 2. Sorry, this one represents our ABC, so ABC, and this one represents our x1, y1, z1. So in place of our x1, y1, and z1, put these numbers over here. So we are going to have a is 2, so 2 times x and then x1 is 2 plus b is 3, y minus y1, which is y1 is already negative, so this place will become positive, plus c, z minus z1, which is already negative, so we have positive here equals 0. For that matter, if you let's check it out here. So this is what you have. So when we multiply through by their corresponding coefficients, I'm going to have 2 times x, which is, yeah, so 2 times x, and then times 2 times negative 2 plus 3y. So we are going to have 2x minus 4 plus 3y minus 12 plus 4z plus 4 equal to 0. And so we are going to have 2x plus 3y plus 4z, and the negative 4, negative 12 gives us negative 16 plus 4, and that gives us negative 12 equal to 0. So when we put it 1 here, we are going to have 2x plus 3y plus 4z is equal to, so this is called the vector equation of the plane. Let's take an example again. The foot of perpendicular drawn from the origin to the plane is 4, negative 2, negative 5. Find the equation of the plane. Now we are talking about origin. And then there is a foot of the perpendicular which is drawn from the origin to the plane. And it is this 4, negative 2, negative 5. And we have to find the equation of the plane. Now we are saying that the required plane passes through the point this, and it's also perpendicular to OA. So we will say that our A is equal to this one, because if it is perpendicular to OA, the position vector of OA written in small letters is this. So since it's perpendicular to OA, it means that our small letter A is equal to 4I minus 2J minus 5K. And our N equals OA. Why are we saying it's OA? We are saying it's OA because the plane passes through the point A, and it's also perpendicular to OA. And for that matter, our N2 is also equal to OA. And therefore, we have 4I minus 2J minus 5K. So this is a substitution. So what you do guys is just substitute the values in. So we have R dot N equals A dot N, and then our N is 4I minus 2J and minus 5K, as well as our A2 is also the same thing. So when you substitute, you are going to have R dot A, which is this, equals this one, A dot N. Our A and our N are all the same, and we have this one. So when you dot this one to this, we are going to have 4 times 4, which is 16, plus negative 2 times negative 4, which is 4, negative 5 times negative 5, which is 25. And that you are going to have this side to equal to 45. So R dot 4I minus 2J minus 5 is equal to 45. Okay. So now in a Cartesian form, our xi plus yj plus zk dots, this one will give us at 45. For that matter, if we dot the two, then it means we are going to have our Cartesian form of the equation as this one dot this, and we get back to the same answer. Equation of the plane when the distance from the origin and the normal is given. Okay, equation of a plane when the distance from the origin and the unit normal is given. Now we are saying that if D is the length of the perpendicular ON, so this is ON, and this ON is perpendicular to the plane at 90 degrees. So ON from the origin O to the given plane. So if we let N be the unit vector, which is normal to the plane in the direction of O to N. So if there is N here, which is also normal to the plane, but it's in the direction of D, Then we are saying that our ON is equal to our DN. D is the length of the perpendicular, which is from the origin to the plane. And there is an N, which is also a unit vector normal, which is also in the direction of the perpendicular vector to the plane too. So it means that our ON here is equivalent or is equal to our DN. So if P is any point on the plane and its position vector is R, so there's a point in a plane and its position vector is R, then it means that our OP, so from the origin to here, is also equal to this. And for that matter, we know that our OP is equal to our R. So when we join N to P, if you join N to P, then N to N, NP, which is also a vector, is also lying on the same plane, and ON is also perpendicular to the plane. And for that matter, if ON and NP are all perpendicular vectors, so where is NP? So our NP is this, and then ON is this, and these lines are perpendicular. Our ON is here, and then our PN is here. So since these ones are perpendicular, then it means that ON dot NP is equal to 0, because we've already said that the dot product between two perpendicular vectors is 0. And then we know that ONP is also equal to OP minus ON, which is equal to 0. So when we expand this one and we dot it with ON, then it means that we are going to have OP minus ON all dots ON, and that gives us 0. Alright, now let's check ON. Where is OP? Our OP is R, and then our ON. So from the diagram, our O to N, so our O to N is also equal to DN. So in place of ON, we put DN here. All dots, another ON, which is also DN. So when we expand, it means we are going to have R dot N minus DN dot N. Sorry, R dot N this one 2 dot N equals to 0. So if you make R the sub, then means that R is equal to N on magnitude of N, and that gives us D. So this is the vector equation of a plane in non-parametric form. Now let's take another question. Now let's talk about the Cartesian form. So we are saying that the Cartesian form of vector equation of this nature is giving us R dot N, which is equal to D magnitude N, and that gives us this one dot this, and that gives us P, which is the same as AX plus BY plus CZ cos D magnitude, which is also equal to D. So this is the Cartesian equation of the plane in non-parametric form. Now let's take a question. Find the vector and Cartesian equation of a plane which is at a distance of 8 units from the origin, and it is normal to the vector, which is this. Okay, so we know that our magnitude for n is equal to 3 squared plus 2 squared minus 2 squared, and that gives us 3 squared is 9, this one is 4 plus 4, and that gives us 17, root 17. So we are going to have root 17. But our vector equation is R dot N equals D of magnitude of N. And then our N is 3I plus 2J minus K, because this is the normal vector. So we have R dot 3I plus 2J minus 2K equals to our distance is 8 units from the origin. So 8 times root 17. So this is our vector equation. Now, in Cartesian form, he said that we have xi, yj plus zk dot the vector given, which is 3i plus 2j minus 2k equals to this. So when you dot this one to this, you are going to have 3x, this one to this. You get what? Because we know that I dot I is equal to 0. So in that case, xi dot 3i gives us 3x. And then this one 2 times this will give us 2y. This one 2 times this will give us negative 2z. This one 2 is equal to, and negative 2 is equal to 8 root 17.